Hello everyone, in this lecture we will discuss about adaptive biasing. Adaptive biasing, why adaptive biasing? Why this biasing? Because it can reduce power dissipation in an amplifier while at the same time it can also increase the output current driving capability. Okay, now here shown in this figure 18, you can see over here that it is very helpful to illustrate the idea that this when VL1 and VL2, these both the voltages, both these gate voltages are equal, then the current source, that is IS1, ISS1 and IS2, are zero, that is they are open, and the differential amplifier DC tail current is simply ISS, the same as in the case of ordinary bias differential amplifier. And if this VL1 become larger than this VL2, the current source ISS1 increases above zero, which effectively increase the differential amplifier DC bias current. And similarly, if this VL2 is greater than this VL1, then the current source ISS2 become larger than increases above zero. And this differential amplifier output current is normally limited to ISS when one side of the differential amplifier shuts off. However, now that the maximum output current is always limited to either ISS plus ISS1 or ISS plus ISS2. Thus, the power dissipation can be reduced using an adaptive bias and slew rate can be eliminated. Okay, because in this case, when these voltages both are equal, this ISS1 and IS2 is 0. Okay, now the current differential amplifier as shown in this figure 19 can be used to implement the current source ISS1 and ISS2. You can see over here, if this I1 and I2 both are equal, I1 is equals to I2, then zero current flows in this M3 and M4. And if this I2 is greater than this I1, then zero current flows in again this M3 and M4. And if this I1 is greater than I2, then the difference of the current I1 minus I2 flows in M3. And this M4 is K times wider than M3, so a current of K in brackets I1 minus I2 flows in M4, where this K is always less than 1. Now, another in this figure 20 shows the implementation of adaptive biasing into the differential amplifier of that discussed in figure 18. Here, the P-channel MOSFET you can see over here are added adjacent to M3 and M4. Okay, to mirror the current through M1 and M2. Okay, that is I1 and I2. The maximum total current available through M1 occurs when this M2 is off, and positive feedback exists through the loop, that is M1, M3, M5 to up to M7. And initially when M2 shuts off, the current in M1 and M3 is ISS. This is mirrored in M5 and M6, and thus ISS1 becomes K times ISS. And at this particular instant of time, the tail current which flows through M1 is now ISS plus K ISS. And however, provided the MOSFET this M1, M3 up to M7 remains in saturation, this current circles back around the positive feedback loop and increases by K. This continues and which result in a final or total tail current of I out will become equal to ISS into in brackets 1 plus K square plus K cube plus and so on bracket close, and it form a geometric series if this K is less than 1, and the summation of this series will be I total will be equals to ISS upon 1 minus K. Now, a final example of this adaptive voltage follower amplifier is shown over here in this figure 21. Here, this amplifier basically can only source current to a load if this V in and V out are equal. This V in and V out are equal, then the current that flows in M1 and M2 is equals to ISS plus ID6, this current and this current. And if this V in is increased, the current in M1 and M3 will increase, and this causes the current in M4 and M6 to increase as well. Okay, which effectively increase the tail current of differential current. Okay, and this result in a large current available to drive the load. Okay, so know that this M7 can be sized larger than the other MOSFET to increase the maximum output current. So this is all about the adaptive biasing. Why we have used adaptive biasing to decrease the power dissipation as well as to increase the output current driving capability of the circuit, and the different configuration of adaptive biasing. In the next lecture, we will study about analog multiplier. Thank you.